Okay, today is going to be the first trip into the wild world of thermodynamics, and basically this is going to be something that is I'm going to go relatively vague for the start of this. You just got to realize that when you get into college, instead of having something that is a 4 or 5 week course, you're going to have things that are single semester to multiple semester courses involving in the same exact topic here. So just realize that I'm just getting you introduced into the topics, the terminology, and how to use it. So let's just start with the word thermodynamics. Alright, now you split it up into what it's made up of here. You got thermo and you got dynamics. When you're dealing with thermo just has to do with heat, measure of heat, anything that involves heat itself. Thermos, thermal underwear, anything that has that therm means that it's involving heat. Dynamics means motion. So when you're looking at thermodynamics, it is literally the movement of heat from one location into another. Right now, here's the reasoning that they have what's called the Zeroth Law of Thermodynamics. I'm not going to sit here and write out the entire thing for you. That is in your book. I would recommend jotting it down in your notes, though. The Zeroth Law says that if A is in equilibrium with B and B is in equilibrium with C, then A would therefore be in equilibrium with C. So basically what that's saying is if we have three different objects here, let's say object A, object B, and object C. All right? If object A is in thermal equilibrium with object B, that means I could take object A over here, could slide it across the top of it, have these two in immediate contact with each other, and there would be no heat change, no heat exchange from location A to location B. Alright? That means not technically that there is no heat moving. Heat may move, but what it means is as much heat is going from A to B as is going from B to A. They just mean that they're in thermal equilibrium, so therefore whatever's leaving is also coming back in. So if A is in equilibrium with B and A is in equilibrium with C, once again you could take these two objects, have them in immediate contact with each other, and if they're in thermal equilibrium, that means that the overall heat, there's no transfer from one location to the other. So if A is in equilibrium with B and A is in equilibrium with C, that means therefore B would have to be in equilibrium with C as well. And once again, all that's saying is basically if A is the same temperature as B, A is the same temperature as C, B is the same temperature as C then as well. So it is an insanely basic concept, but literally it's called the Zeroth Law for a reason. Literally. If A is in equilibrium with B, that means that there is no net heat moving from A to B. If A is in equilibrium with C, that means there is no net heat moving from A to C. So therefore, if you have the Zeroth Law being in effect, that means you don't have thermodynamics. There's no actual motion from one point to another. The reason that it's the Zeroth Law is it literally is the background for everything else. So if you don't have this, nothing else can happen from there. Okay? Now, one thing that commonly gets misconstrued here is two terms that get interchanged but shouldn't be. Temperature and heat. Alright? Key thing here is temperature is not heat. They are not the same thing. They cannot be interchanged. One cannot be used for the other. Basically, when you're talking about heat, you're talking about the amount of thermal energy contained by an object. All right, now that thermal energy is in essence, pardon the bell, thermal energy is in essence the amount of kinetic energy of the individual particles. The more that these individual particles vibrate, so here's my individual particle, the more that this thing vibrates, the higher the heat level. The less it vibrates, the lower the heat level. So basically the thermal energy, kinetic energy, really relatively similar in that regard. So heat is just the amount of thermal energy contained in the object. Temperature, however, is a little bit different. Temperature you can kind of think of as a driving force. All right? Temperature is more of a measurement than anything else of the amount of heat contained in an object. All right, now I'll get more into this driving force thing in a couple of minutes, so just leave that one go. But think about it more right now as just a measure of the amount of heat contained in an object. All right, now just because an object has a higher temperature doesn't mean that it has more heat. Once again, we'll get into that a little bit further down the road. But temperature is kind of the driving force between A and B. All right, one key thing that is of note. When we're talking about temperatures in here, we absolutely positively are going to be using the Kelvin scale. Now there's a bunch of reasons behind that. The first one is that this is an absolute scale, which means that there's no negative numbers, which is going to be very, very useful when we're talking about some of the math down the road here. All right. So it literally goes from absolute 0, which is 0 Kelvin, which is the point at which all motion would thereby inherently stop. And it goes up to pretty much a limitless value. It is graded the same exact way as Celsius or centigrade. All right. So in other words, 1 Kelvin is going to be the exact same size as 1 degree Celsius or 1 degree centigrade. Okay, so they're using the same scale, they're using the same values, but instead of having negative numbers, which we would have in here, those negative numbers dissipate when we start at the point of 0 motion. Okay, so, all right, Kelvin is a very useful tool. And we're going to use this a lot because it's not going to monkey up our math too much. All right, now, the one big thing is no Fahrenheit. I'm not even going to spell it because I always misspell it when I try to. All right, but do not use what we understand it to be. Fahrenheit. All right, a lovely assistant just helped me out with that one. Do not use Fahrenheit. All right, do not use Fahrenheit. The reason is the gradation of it. 1 degree in Celsius, centigrade, or the value of 1 Kelvin is not equal to anything in Fahrenheit. All right, the 9/5 or 5/9 plus or minus 32. It's a real pain in the neck trying to go from Fahrenheit to anything useful. Now, for the most part, we might do a lab or two in here, and when we do that, we will use Celsius/Kelvin measuring systems. Do not use Fahrenheit. I know it's what we're used to, but scientifically it's just a little bit less useful than anything else that we've done. Okay, so please, please, please stick with the Kelvin. All right, now let's get into the actual usefulness of this stuff. First thing that your book talks about is thermal expansion. All right. Thermal expansion. There's two different types that we can deal with. First one is length. Second one is volumetric. These are insanely similar. That's why I'm putting these on the same exact board here. Okay? Now, when we're dealing with thermal expansion, what that means is the length of a material is actually going to change based upon the temperature of that material. Easiest way to visualize this or to think about it is if you look outside and look at the telephone poles. The telephone poles, the wires going in between them, will be much more slack in the summer and much more taut in the winter. That is because the actual material itself, the copper in that wire, is going to stretch as it gets hotter. It is going to make itself shorter when it gets colder. Okay, the same exact thing happens to the same extent when you're talking about bridges. If you've ever noticed, this is kind of off to the side, I'll erase this when I'm done, but if you've ever noticed as you're approaching the edge of a bridge, you're going to see these things that kind of look like intertwining fingers. One will be on the base side of the bridge, and the other one will be on the bridge mount side of the bridge. All right, these are what are called an expansion joint. The bridge itself, even though you would really like to think of it as permanent and being exactly where it should be at all times, that bridge itself is going to expand and contract in the winter and the summer months to make the bridge larger than or shorter than it originally was. So they put these teeth in here, this expansion joint, in order to allow that material to actually change size without destroying the entire bridge and making them rebuild it every single year. Right now, length. For length expansion, delta L equals L alpha delta T. Right now, the most common mistake that I normally get out of people on this one is, let's say that we take a 100-meter long length of wire and we increase that length of wire's temperature by 100 degrees Celsius. You go through and do all this stuff, and then you find out that delta L is 0.2 meters. A lot of people screw up and think that that's the final answer, but the delta L just tells you literally the change in length. It is not the final length. Okay, so if you find that it is expanded by positive 0.2 meters, then your total length, your new length, is going to be L plus delta L. Or if you found that it is shrunk by 0.2 meters, it would be L plus negative delta L. Literally, this is going to get larger in a positive or smaller in a negative. That all happens with this little guy right here. The key thing to remember anytime we're dealing with a delta, right, in this case, it's going to be delta temperature. That is going to be your final minus your initial. When you do that, let's say if the temperature is increased, that means your final temperature is going to be greater than your initial temperature. Therefore, this end result will be positive. If this is positive, that means your delta L is going to be positive. If you have it the opposite way, where it's getting colder, your final temperature is going to be lower than your initial. So therefore, the temperature, small number minus big number, is going to give you a negative delta T, which is going to give you a negative delta L. Okay? So just remember that this is the overall change in length. It's not telling you the new length itself. All right? L, this is just your original length. Now this little guy right here, this is the only thing that is really new and might be confusing. This is what is called the coefficient of linear expansion. All right. Now the coefficient of linear expansion is literally just a coefficient. Coefficient is just some set solid number. Now, if you were to actually go back and solve for what this value would be, it is not exactly a linear relationship which would make this a constant, but it is close enough that we can simulate it as that, as long as the delta T is not too dramatic. Okay? So, this is a handbook value. In other words, you can find this anywhere. You can normally find this on the internet if you just search for coefficients of linear expansion. Also, there's that ancient book that I have on my desk, that CRC Handbook of Chemistry and Physics. That will have a whole bunch of coefficients of linear expansion on that. That just means that every individual material is going to change its size slightly differently based upon the amount of heat that is, or the amount of temperature change that has been impacted to it. Right? Metals are going to change differently than non-metals. And basically, each individual type of metal is going to change differently from itself. And then delta T is just change in temperature, which we already talked about right here. So, nothing too crazy here. It's literally a plug and chug when you go from here on. You'll probably have an original length. You'll be given a material with which you can look up the coefficient of linear expansion, and then you'll be given the temperature change data. Now remember, most of the time that you're doing these temperature changes, They're normally in engineering type courses, in some physics type courses, they're going to normally give you this value in Celsius or centigrade. The good news is 1 Celsius is equal to 1 Kelvin, 1 centigrade is equal to 1 Kelvin. So literally, if you know how big the jump has been from one point to another, then it doesn't really matter what units you're in here. Celsius, centigrade, Kelvin, it really doesn't matter, but I do want you to try to get into the habit of using Kelvin everywhere possible. Okay? Now, rather than insulting your intelligence here, I'm going to put the equation for volumetric up here. Delta V equals V beta delta T. Same exact setup here. This instead, though, instead of being a change in length, it's now a change in volume. Instead of this being original length, this is original volume. Now, beta, new little devil. This is our coefficient of volumetric expansion. Right? Now, the beta value is not something you're not something you're normally going to find in a handbook. But you can interpret it out of a handbook. All right? And delta T is the same exact thing. But this beta value is going to have a general trend where beta is 3 alpha. Now, here's why beta is 3 alpha. Let me get a new page up here for it. All right. If we're talking about something like a wire, when that wire expands, it only has one option in the direction in which it can expand. That wire can only expand in this singular direction, this linear direction. All right. If instead we have something that exists in three-dimensional space, now this face can expand left and right. This face can expand up and down. And this face can expand in this direction here. Volume, length, width, height. So what's happening here is you're multiplying your new length times 3. So the reasoning behind alpha being so closely related to beta is because you now have 3 different directions that this can expand itself into. Instead of just traveling in that singular line, it now can expand itself in those 3 dimensions, and to account for that volumetrically, you got 3 times as much. Okay? That's how those two are actually tied together there. All right. Now, okay. So, that is not very difficult on the math side of things. I will have 2 practice problems for you to work on. I'll have those set up for you tomorrow. I'll just let you know what they are. I just forgot to jot them down about which ones I wanted you to do. Now, next thing. The relationship between heat and temperature. The key thing to remember here when we're talking about the relationship between them, number one, they are not the same thing. Temperature is kind of the driving force. Heat is what actually moves. Okay? So, temperature differences drive heat from high temperature to low temperature. You can actually test this in a very low-tech experiment at home. Take a glass of water, leave it sit out on your table. If heat goes from high to low, I'll tell you what, take that water, boil it first. Put it in a cup on the table. If temperature goes from high to low, that means eventually that cup itself is going to cool down to the same temperature of the room with that air, with the air itself around it going a little bit up in temperature, but not dramatically. If it were going the opposite way, what that means is the hot cup of coffee in the room will steal additional heat from the room itself, causing the coffee to become hotter and the room itself to become colder. Now, we can't actually force that. That's how heat pumps and refrigerators work, but we're not going to worry about that too much right now. Now, the thing that we need to know is, well, temperature we already talked about is in Kelvin. Heat or thermal energy is going to be denoted as a capital letter Q. Okay? Don't know exactly why they decided to go with heat to be the letter Q, but hey, it works. So, let's not fight it. Now, remember, heat is not temperature, but heat is driven by temperature. Okay? So, now, let's look at how this heat actually works and how we can look at what's actually going on here. All right. Now, some of this might be a little bit of a review from some of the chemistry courses you guys might have taken over the course of your career here. Some of you might have unfortunately had almond for chemistry. We're not going to hold that against you. But there are two general equations that are going to work with the total amount of heat that is changing place here. Q equals C delta T. Now, I am going to caution you. Use this as a capital C. Surprisingly enough, a capital C and a lowercase c mean very different things when we're talking about this. Q equals C delta T, or Q equals M delta T with a lowercase c. Yeah, I know. Insanely similar, but still different enough that we need to talk about them separately. All right? Now, it is very case specific. This is a capital C. This is a lowercase c. When we're talking about a capital C, the capital C is referring to heat capacity. In other words, it is talking about how much heat can be contained in a unit of moles of this material. Okay? When you're talking about lowercase c is what's talking about specific heat. Now, the specific heat is literally talking about the heat capacity, the amount of heat that this thing can contain per unit of mass. Okay? So this is just generic to the material. This is per unit of mass. I will tell you that we are going to use this much more often than we're going to use this guy right here. Just because when we're talking about the scientific case, we're not exactly so interested in how much heat this thing's going to absorb. We're more interested in exactly what this is doing to our individual sample. Now, word of caution about these Qs before we get too much farther. The units on it. There are a lot of different units that you're going to see with this. Q could be measured in joules, which we did with work before. All right. Sometimes it'll go into megajoules or some very, very large variations on joules, but it is a possibility for joules. Another possibility is the calorie, which surprisingly, if you're talking about the food that you're eating, that's what calories actually mean, how much energy you can get while your body burns it. Now, the third possibility, we're not going to deal with this one too much, but I will refer to it, is what's called a BTU, or a British thermal unit. BTUs are normally used in devices that are used for flash heating or flash cooling. Air conditioners will be rated in BTUs. A lot of times gas grills, propane heaters, things that cause a certain size room to heat up, they're going to normally be measured in BTUs. Now, here's the dig with this stuff. A lot of this is going to be determining exactly what units show up on here. There are conversions from one point to another. I will go into those in a future video, but realistically, use this to set your units. Your specific heat or your heat capacity, that is going to be what's determining what your units are. Because you're going to find this as a handbook value. Each individual metal, non-metal, whatever you're talking about, is going to have a different specific heat, a different heat capacity, and this is going to determine exactly what units everything are. All right? So this will end up being like joules per mole Kelvin, or calories per kilogram Kelvin. When you have this stuff here, this is going to dictate what units are going to end up. You can convert later, you can convert your C, however you decide to do it. Just make sure you show your work on it. Okay? Nothing too crazy on this. It's not insanely difficult. The hard part is just getting things set up and getting things where you need them to be. In your book on pages page 485, there's a brief list of a few of the different specific heats, molar specific heats of some different materials, elemental solids, yada, 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 some liquids. Most of the practice problems that we're going to be doing are going to include those values right there. Okay? Now, this is basically telling you how much heat. Here, I'm going to kind of put this in a different color to denote it separately. How much heat will make this size sample of this material change this much temperature. That's the easiest way to think about it. How much heat do I need to make this much material of this individual specific material change temperature by this much? Now, the fact that the heat capacity, the specific heat of different materials is going to be very different, that means that the amount that it is willing to transfer from one location to another is going to be very different. That's why you're going to notice that if you're talking about cookware that you put on top of your stove, most of the cookware you put on top of your stove is going to be metallic in nature: copper, brass, iron, steel. Most of the stuff that you put in the oven, however, well, some of it might be metal, but a lot of the stuff that you see as a baking type situation, you might find glass, you might find stoneware, stuff like that. And that's all based upon the amount of heat that it is able to transmit from one material into another. So that's how this stuff works out. This all does this for basically solids, liquids, and gases. I think I put too many S's in there, but I really don't care. Okay, so same exact thing. It is going to cause a solid to increase its temperature by this much, a liquid to increase its temperature by this much, a gas to increase its temperature by this much. Surprising thing is that this C value, whether it's lowercase c or capital C, will change based upon the state of the matter itself. So water is not going to have the same C value as steam. Water is not going to have the same C value as ice. Okay? Now, the other thing that we need to worry about is phase changes. And then that's going to wrap things up for this video lesson. I will do a practice problem on another one for you guys to see. Well, that's not how you spell changes. Changes. I will do an additional practice problem on a separate video. I will put that at the bottom of this page as soon as I have it up. All right, now, when you go from one phase to another, you are basically... Here, I'll put the equation up on the board here. Q equals Lm. Think about it like this. It takes energy for water to boil. It takes energy for 100 degrees Celsius water to turn into 100 degrees Celsius steam. It takes energy for 0 degrees Celsius ice to turn into 0 degrees Celsius water. You can kind of think of this as kind of the fee or the toll for phase change. Right? It's the amount of energy that's required to go from one state into the other. Okay? So, all right, when you're dealing with this here, Q is still heat. Nothing new there. This L right here, some people just call it some people call it the heat of transformation. I've also seen it called the latent heat of transformation. I like the latent heat of transformation. The book doesn't use that, but I do. I'll tell you why in a second. Alright, now latent itself kind of means that nothing is really happening here. But literally, we need that heat to go in for this amount of material to change its state from one to another. Now, you're going to notice a few different things here. In your textbook, on page numero 487, there are latent heats of melting, and there are latent heats of boiling. Which literally, latent heat of melting, latent heat of boiling. It takes a different amount of energy for a material to turn from a solid to a liquid than it would for a liquid to a gas. Okay? So, literally, all it is a handbook value once again. People long ago decided to do all these calculations for you to determine all this stuff up so that you don't have to do it. So, hey, let them do it. Okay? So, literally, all it is, this is your mass of the sample. This is the heat in, and this is the amount of energy that's required to turn this amount of mass from one state into another. All right, I will start with a practice problem. You will have that up and ready to roll, hopefully by end of day today. Probably not, though. I'm not holding my breath, but it will be ready for tomorrow. Okay, there's also a second video lesson which follows this one up. That one I already tested and is running on the website, so you can try that little guy out at your leisure. At the end of that second video are 3 practice math problems. I want you to try to have those done for me. The schedule for when they are due is up on the calendar on the course website. Best of luck to you, and if you have any issues with it, please let me know ASAPly so I can help you out as best as I can. All right, good luck, and we'll see where we end up.